superconductivity.
Thank you very much. Well, thank you very much. And this is a hard act to follow. I don't have the clicker. Okay. Now I have the clicker. I learned to buy clothes with pockets now. So it's a real pleasure to be here. I want to thank the organizers. Ali, you're doing a great job. All the organizers have, and it's a beautiful place. And so I'm a little worried I'm keeping you away from your welcome cocktail, but Ali said he's moving things back a little bit, so you'll still get your cocktail. So anyhow, the title of my talk, it's a little longer, but I'll just say it shortly. I came up with a fun analogy a few years ago, and I'm going to talk about that. So I'm doing a lot of different things right now. All right. There we go. So why do I have this title? I have this title just because I've been doing quantum materials for many, many years, and this is an overview that I looked at that helps us understand how complex this problem really is. So it's a really public engagement, and it's become sort of my view from what I fly a lot, so like at 35,000 feet up, what it looks like. And so one of the things I like to point out is that in quantum materials, there are many, many unsolved questions, and that's what I'm going to bring up most here, if I get to it at the end. And these questions are certainly no less fundamental, and that's a point that I really want to bring home, than anything you have in cosmology or high-energy physics. And I like to point out that there are many things that we have in common, and I'll do a fun analogy. Don't take the analogy too seriously because I really don't know enough about it. But colliding black holes create gravity waves on the order of 10 to the 26 meters wide and 10 to the 49 watts. And a lot of these quantum materials are things that form clumps, like electronic nematicity, stripes, et cetera. And these are on the order of 10 to the minus 10 meters or 10 to the minus 21 watts. And so the difference is in 10 to the 36 in length and 10 to the 70th in power. I'm not saying they're identical, but a lot of the mathematics and a lot of the ideas really do correlate. So the outline is I'm going to spend a lot of the time talking about the National High Magnetic Field Laboratory. I'm finding since I've been there, that's what people really want to hear about, how broad it is, how interesting it is. And then I'm going to tell you what the definition is between a conventional and an unconventional superconductor. And it really helps, especially young people, put these in a different perspective. If I have time for my analogy, I'll do that. I probably won't have time. This is something that I won't be talking about here, but if I have time, I'll flash a slide. And there's a lot of great progress that's happened in quantum materials, and still a lot of questions to go. And I like to warn you that I love to use analogies, pretending if you're swimming in a lattice or something like that. But if you push any analogy too far, it breaks down. And I like to bring that up because in quantum mechanics, we have to use analogies. And the most favorite one is the Bohr model of the atom. We love it, we teach it, we use it, and it's completely wrong. So there are useful analogies. Now, onto the National High Magnetic Field Laboratory. No one could remember NHMFL or NHMBFQ, anyhow. So we just call it the Magnet Lab or the Mag Lab. So our mission is to operate a world-leading high magnetic field user program. We are primarily a user program. Carry out in-house research in support of the user program. And we do have some terrific in-house research that's going on. Maintain the facility and develop new instrumentation. And I'll show you some things that are really moving along there. And another thing, because we're supported, our core grant is from the National Science Foundation, not from the Department of Energy, not from Commerce, et cetera, we are charged with having a strong educational and outreach program. So moving along, I keep doing it on this one. So this is just to give you an idea of the National Magnet Lab. So we have 3 campuses. The main campus is in Tallahassee, which is northern Florida. I'll show you a map in a minute. It's basically southern Georgia, and it's a very, what did I do wrong here? So if you hold, okay. It's a very, very large facility. If I go from my office to my lab, my Apple Watch rings close in half a day. It's really, if you have a chance to see it, you really can't really appreciate how vast it is. Now in Tallahassee, there's a map here with Florida State up there, there's the United States. We have the strongest magnet in the world within error bars, which is a 45 Tesla hybrid magnet. By hybrid, we mean it's a combination of a resistive magnet and a superconducting magnet. And we can also do 21 Tesla NMR research. In Gainesville, at the University of Florida, I'll be showing some examples here. We have 2 user facilities. One of the user facilities is the high B/T facility, which doesn't go as high field, but it goes to very low temperatures. So you have the highest B/T in the world. And then people love these things, so I'm going to show you several examples where we do advanced magnetic resonance imaging. It's called AMRIS, the Advanced Magnetic Resonance Imaging and Spectroscopy Facility. And we do MRI up to 21 Tesla, and we can do in vivo MRI. And I just came from Los Alamos, which is why it took me almost 53 hours to get here. And at Los Alamos, we have a 101 pulse magnet, which is the most reliable pulse magnet in the world. However, here's a great picture. So this is the rotor that produces the high magnetic fields, and that's a normal sized person. So if you can, it's really big. And if you're interested, I've got a long history of it. I can share it with you if I have time. But anyhow, it's about 101 Tesla pulsed. So here's our Delta Airlines map of the Magnet Lab. So what we have here is that in 2019, the Mag Lab hosted over 2,000 users in over 152 institutions. That number has gone up. We had a little hit because of COVID, but the numbers are back up higher than ever. And here are the facilities that you can see the people. This is the 2019 Delta Airlines map. That's Gainesville in the light blue, and purple is Tallahassee, and the red lines are Los Alamos. Okay, so we see people from all over the world. About 300 institutions, that's probably increasing. And one thing that I'd like to point out, if you look at some of those lines there, you'll see that they originate in Wuhan, in Hefei, in Toulouse, in Dresden, places where there already exist magnet labs. And we do work in each other's labs, and it's a great collaboration. But they want to use our probes, and they want to use our magnets. I want to point out also, I'm going to advertise this, newcomers are welcome. Yes, we're oversubscribed, but we're looking for new people all the time because we want to have turnaround and diversity. And typically every year, about 25 to 30% of our PIs have never used the Magnet Lab before. So our Mag Lab faculty are very good at working with first-time users. And you have to write a short proposal, and you're welcome to contact a Mag Lab faculty, I'll show you a slide later, and ask them to help you write the proposal. We just want to help you get the science done. And so we'd like you to come and visit. And I always say it's free to use. If your work is publishable, it's free to use the facility. You just have to get there. And if you won't be there for too long, you can stay with me. I have a big house. The other argument that we have, why would the NSF put that money into a facility? Well, the bang for the buck, the respected papers per dollar is really very high. And we also do things that you just can't do in a single PI in their home institution. And I'll show you some of the reasons there. Now we have here just showing that we have different kinds of magnets. And so this is our short pulsed. Our short pulsed is being rewound now. They found a problem with it. It's a great story. But while it's being rewound, we went back to what the other labs use and use capacitor banks. They're less reliable, but we now have a 75 Tesla pulse field that we just built while this thing was down. But you can see we have all these magnets. So we will be building the 60 Tesla magnet. We have the 45.5 T. That's a DC magnet, by the way. I mean, that's not a superconducting magnet. One thing that we won the R&D Top 100 of the Year award that was just announced was we have a 36 Tesla all superconducting magnet user facility. This is way above what anyone can do. So we're really proud of that. It's very useful. Some of our big hits, I'm not only besides the 30 Tesla, we have something called a 36 Tesla series connected hybrid. Without going into details, it's very homogeneous, very stable, and you can do imaging at 36 Tesla. And some of the other things, this here was in 2018, they made a 45.5 high temperature superconducting test coil. And among other things, and the success in our 30 Tesla all superconducting magnet, the National Science Foundation just funded us the design funds for a 40 Tesla superconducting magnet. So we're very excited about that. Now this is the fun part where I'm going to talk about some science, and there are going to be overviews, and I don't know if I can answer all the detailed questions, but as chief scientist, this is part of my job. Our main areas of research are materials, energy, and life. So I'll just show you some materials examples. So this is one that really had people, it just started a whole new field of research. It's this heavy-fermion, uranium-tellurium, I do this all the time, don't I? Uranium-tellurium-2. And what was found was that if you apply, as many of you know, I'm not going to be giving a public lecture, I'm going to assume you know what a superconductor is, that if you apply a field to a superconductor, you break the superconductivity. So we have here, as a function of angle in the uranium-tellurium-2, if you apply a certain field, this white area is where it's not superconducting anymore. Okay? If you then increase, and what's interesting at this angle, the superconductivity lasts up to 35 Tesla. Now let's change angles here. As you go into a certain angle up above 35 Tesla, all the way up to 60 Tesla, so this was done both in our DC and our pulsed field user facility, they found that a new kind of superconductivity evolved. They called it Lazarus because it's woken up, you know. But basically, this is completely new, and it's not understood. It was a complete surprise. It looks like a triplet superconductor. There's a lot of studies going on, and it's been a very interesting and fruitful area of research. This one I'm glad I threw in here because this Ahmet might be interested in. So this is all still prototype. This is some of the spin transport they were doing on our electron magnetic resonance area. So this is EMR. They also call it electron paramagnetic resonance, depending on where you've been. But what we have here is an antiferromagnet that's attached to a non-magnet, okay? So this is a heavy metal, platinum, magnesium difluoride, and you send in terahertz radiation, and you get a spin transport across, and you can bring out ultra-fast electrical signals. So it's spin transport through this platinum. Now, what happens is it's 2 to 3 times orders of magnitude. It's 2 to 3 orders of magnitude faster than your standard ferromagnetic devices that people study. And the reason for that is this coupling is due to exchange. It's not due to magnetic anisotropy. So that's been a fun thing to study. So it's promising for spintromics devices and who knows what else. So this is just an aside more on materials. I'd like to point out that superconductivity and high energy physics, if you don't know, they've been buddies for decades and decades. And here we were making, I wasn't, but they were making superconducting devices for bubble chambers. And now we're playing a major role in the high luminosity upgrade of CERN. So, I'm going to say also this, that the largest funder of superconducting materials on the planet is the Department of Energy's High Energy Physics program. And they help keep our Applied Superconductivity Center going. And so our Applied Superconductivity Center and our Magnet Science and Technology Centers, these are 2 labs that aren't user facilities, work very closely with the high energy community. And we've invented some new materials. So most of you probably know that if you go into an MRI, the standard, if you're using a magnet, is niobium titanium because it's malleable. The A15s, like niobium 310, have a higher TC, a higher HC2. I mean, not a higher TC. Yeah, they do. A higher TC, higher HC2, and higher JC. But they're harder to use. They're compounds. So if you have to like wind them and then fire them. But we've done some work in increasing the JC so much of niobium 310 that is being used in the high luminosity upgrade, which is expected to increase the luminosity in CERN by a factor of 10. And those magnets are being shipped. It's a combination with the Magnet Lab, Fermi Lab, Argon, and also LBNL. Oh yeah, and then we actually have a new one. There's a new niobium-3 tin with hafnium doping that we're looking at because that is very promising for the linear collider, LHC. And I want to point out that I've seen Fabiola, I've met her several times, I've seen her give talks, the Director General of CERN, and the Mag Lab is all over her slides, and she says the only thing that's limiting our luminosity are the magnets. So it's nice to be useful to other fields. Now I'm going on to examples for energy. These I think you're going to like. Most of this you wouldn't have known about. And I love to focus on our ion cyclotron resonance facility. It's also called Fourier transform ion cyclotron resonance, ICR. I did not even know about this until I started coming to the Mag Lab a lot more. So what this is a mass spectrometer that is on steroids. It uses a 21 Tesla magnet, and you can you throw and you spit in a little complex fluid, start the cyclotron resonance, chirp it, and you get a band like this, a comb like this, and this comb, you can separate out in complex fluids and get mass resolution of about an electron. So why do you want to do this? Well, this was developed first for petroleomics. So, for instance, the most complex fluid on the planet is petroleum. So if Exxon and BP are drilling in the Gulf of Mexico and they both hit oil reserves, they want to know if they hit the same reserve or not because it costs $1 billion to dig a hole to go looking for oil. And so this technique, and we do work for them, and they pay for it. They don't get to use it for free. But we can fingerprint the oil well enough to know exactly where it came from. It's also used for forensics. If an oil spill happens, even if it's much, much later, we can look at the makeup of the oil and tell you exactly which oil head it came out of. And so then we've applied this to a couple other things. What I won't spend a lot of time with, I'll have more examples of sustainability, but proteinomics. So this is so accurate that you can actually tell the difference between folding and proteins. The most popular protein is the p53. As many of you might know, that the folding of a protein determines its functionality. And by doing a hydrogen-deuterium exchange, you can tell what the folding is and tell if p53 is, and it's well known that this can be a completely healthy, neoplastic, or malignant protein. So that's very interesting. And then finally, for climate change and sustainability, it turns out we also look at like the second most complex fluid, which is dissolved organic carbon and PFAS. So I'm going to say a minute about those. So here's one thing that we do here, looking at climate change. So you go up into the Arctic and you take samples, and you can tell how the carbon in the ice and in that area changes as a function of latitude and also time. And you can tell, for instance, this is what no one else can do in this, is you can tell if the carbon, dissolved organic carbon, is in the shape of an island structure or in the shape of an archipelago structure. And one's good and one's bad. To be honest, this is the one that's better because you can separate. The water soluble, which is the one that's so difficult to get, it's so complex, is you want to be able to get, this is the good one because you want to be able to get the tar out of the carbon. So this is an example, and you're looking at these things that are about 1 electron mass separated. Okay, so here's another one that just came out a few months ago. So when you leave, there's something called PFAS, which are long-chain fluorine-containing molecules, and they're very bad for you. They're carcinogenic and they're terrible, and they're in plastic bags, they're in a whole bunch of things, they're in asphalt. And that's something that Amy McKenna at the Magnet Lab studies in great detail. And she found something recently, which was that if you leave a plastic bag out in the sun, it was thought that PFAS never decompose. the PFAS does decompose. They're studying those decomposed elements now, and we don't know if those decomposed elements are more dangerous than the PFAS are, which are already pretty dangerous. And there's a lot of, I can go on forever on this, but rather than doing that, rather than going on to this, and I'd love to talk about it, I want to talk about some of the life examples. These are all from, everything I showed you up to there was either mostly from Tallahassee, a little bit from Los Alamos. These next ones are from University of Florida in our Amherst facility, which is in the McKnight Brain Building. It's a fantastic facility. So here's one example. So how many people have been in an MRI? Probably anyone over about 25 has, yeah. So the best thing about an MRI is you get to go inside of a superconducting magnet, right? That's very cool. But the MRIs that you get in the hospital are 3 and 5 Tesla. There's a lot of reasons for that. One of the reasons is that you can do it, okay? Another reason is that if you don't really want to go too much higher, because if you increase the magnetic field, you have to increase the RF field of which you're measuring, right? You have a resonance conditions between the field and the RF field in which you do the magnetic resonance imaging with. So typically what you have is that you can see about a 1 millimeter resolution. But if you go up to what we can go up to, which is 21 Tesla, you can go to micron, a 10 micron resolution. So you can see things much better. And so you don't want to look at too many living things. You can for a short time. But here's an example of imaging by MRI of a frog brain. So now we can see subcellular structures. So one example is that still using 21 Tesla at the Magnet Lab, we have shown that you can actually, so if you're looking, Alzheimer's disease is believed now to be generated from plaque amyloids that build up in the brain. And it turns out that we could now have the earliest detection of this. We can't do it with human brains yet. These are still rat brains and small animal brains. The biggest diameter is about this much for this in vivo stuff. But what happens is that when the plaques form, they create microhemorrhages. And boy, when you do MRI, that's what you can see, right? When you do MRI, you pick up the hydrogen. So here you're looking at, I don't know if you know this, but when you do MRI, you're looking at protons in the hydrogen, and that's what you're imaging. And so if you increase the field, you have to increase the RF. It's a much higher frequency, so that is a shorter wavelength, and it gives you higher resolution. So the plan is, and in Florida we do a lot of work for aging, the plan is that if you start getting that's the plan. If you start getting other symptoms of Alzheimer's, like loss of taste, et cetera, it might be COVID, but there are other symptoms. Maybe we could look for early plaque amyloid in the brain. So another one that's very interesting. You know what? I should do this one first. Yeah, I should do this one. No, I'll go to this one. No, I'll go to this one. I just changed my mind again. So here's something that I put in here because it has to do with gadolinium nanoparticles. So it turns out that one of the things that people are looking at for stroke, for healing stroke damage or any brain damage, is injecting stem cells. This is a very new result, was that what they were able to do, and in vivo means we're looking at a living mouse, okay? A living mouse they had a stroke, and you can inject stem cells, but you could label them with gadolinium, attach them to the stem cells, and then you can see how they move around the brain and understand where the damage is. So that's extremely new at the Magnet Lab, and the one that I went over, which everybody loves, is this one here, which is for cancer detection. And again, this is still a prototype. We do something called, so I mentioned that when you do MRI, you're looking at water, you're looking at the hydrogen in water. They call it proton MRI. Okay? But what if we decided to look at something besides hydrogen? What if we call that unlocking the periodic table. So in all of our resonance facilities, MRI, NMR, and ICR, we can look at all kinds of different isotopes. So here's one example, and that is looking at sodium. Now, if you look at sodium, it's a lot heavier than hydrogen, so you can use a lower frequency to do the resonance, so you're going to have lower resolution. but you're specifically focusing on the sodium. So here's an example. It turns out, something I learned when I got to the magnet lab, you can buy a rat with a brain tumor. Okay, so here is the image of a brain tumor. It's the sodium in the image that you're looking at. This isn't the proton, this is an MRI. We're specifically looking at the sodium. Now, it turns out that when cells are dying, they uptake sodium. We don't completely understand why, but they do. So what you do is you image the sodium, you image the tumor, and then you give it chemotherapy, wait 4 days, image it again. Nothing happens, you do that again. And at some point, if the chemotherapy causes the sodium to light up, that means it's uptaking sodium, the cells are probably dying, and that might be a good direction to go, good regime for the chemotherapy. Now this is prototype, but boy, this could certainly be promising in the future, and I'm sure we've all been touched with people that have had to go through this. And to make it shorter and to see the efficacy of the chemo would be very, very important. No, that is the right way. Okay. So this is, just go online, go see what you have. We're redoing the website now, so it's even easier. Pick out what magnets you want, look around. Also with our education stuff, and we'll help you write it. And it's just fun to look around. And there's all this educational stuff, Magnet Academy, stories, et cetera, et cetera. And I think February 25th, we're having our open house where we have 10,000 people show up. Come on over, okay? It's really fun. So anyhow, now I'm going on to the superconductivity part. So I hope it doesn't last too long, but so I just wanted to point out that you did see the bubble chamber before, and in every high-energy physics talk you've ever been to, they always show you a picture of the ring. So this is the superconductivity, so I have to show you this figure of Cameron Lachonis discovering superconductivity. I'm required. It's in the job description. So this was a great story because it was serendipitous. So much stuff in superconductivity discovery, new materials, new superconductors, new ways to grow them. It's really so much serendipitousness. And we're all working very hard to do predictive design, but that's the story. So before Cameron Lachonis measured this, what happened was he and Giles Host, who doesn't get credit, he was the technician at the time, but he went on to start Phillips Laboratories, so I guess he did okay. No one knew what would happen so they managed to liquefy helium, and out of curiosity, they decided to cool down a wire they made of mercury. And lo and behold, this is what happened, is that, as you all know, that the resistance dropped to 0 at a little over 4 degrees. Their measurement scheme wasn't so good. No one had predicted that. They thought that maybe if you lower the temperature, the resistance would go up, it would go linearly to 0, and people had their theories, but this was not expected. That was 1911. It wasn't until 1957 that the microscopic theory of superconductivity was solved. Okay? And it looks so simple now, but it was impossible. And it was a worldwide effort, and Bardeen, Cooper, and Schrieffer managed to, publish the paper, and it's very exciting. And you know what? It worked. It's one of the 2, maybe 3 solved problems in correlated electron physics. So that problem is solved. That's conventional superconductor, and as I think probably all of you know, the answer is not just the BCS theory, but the BCS electron-phonon. It's the electrons moving through the lattice, and good superconductors have strong electron-phonon interactions, and that's the basic idea, and we kind of understand that. But then these 2 geniuses, Frank Steglitz, discovered something called heavy-fermions, and heavy-fermions, I mentioned them earlier, are materials that due to electron-electron interactions, not electron-lattice interactions, electron-electron interactions, the mass of the electron measured thermodynamically is huge. The one that I was growing thin films with was cerium copper-6. It had an M star of 1,000. The one I'm studying a lot now is 85 or 120, but you can't get that from the band structure. And then what happened was Gil Landras started, he was really big on this pressure stuff. I just talked to these guys recently. Big on this pressure stuff, and he discovered this phase diagram. Okay? So this phase diagram is super important. We talk about it all the time. If you've worked in high TC, you're very, very sick of hearing about it. And, but this is it. And that what we have here on the y-axis is temperature. On the x-axis is a thermodynamic variable. In this case, it's pressure. And I don't do pressure measurements. I have done, but mostly I do doping, and I'll show you some examples. But what we have here that's really so interesting is that what's so surprising is that we have antiferromagnetism on one side and Fermi liquid, a normal metal, on the other side. And here's the crossover across this line here. And then when you get down to lower temperature, these phases fight each other, which is determined to be a quantum critical point in most of these things, and this dome of superconductivity appears. Why does that happen? Very interesting. But the fact that it's near magnetism, as we all know, conventional superconductors really hate magnetism, right? And so, why does magnetism all of a sudden good for superconductivity? And it became clear that BCS electron-phonon coupling couldn't be the only story here. So moving right along, you've seen this. If you've been in superconductivity, you've seen this a million times. I just like to remind everyone about this. Everything in red is solved. Okay? Everything in red is solved. These are electron-phonon BCS-coupled superconductors. And it's believed here that the high-pressure hydrogen sulfides and superdeuterides are all electron-phonon BCS. Everything not in red is not BCS. I've only put a very small fraction. I mean, because I'm lazy. I took this from a study I was on a million years ago. But you know, we have here the high-temperature cuprates. We have the iron-based superconductors. We have the heavy-fermions. You know, the carbon, all kinds of things. I didn't list the organics. There's a whole bunch I didn't list here. I'll mention them later on. It's like each one of these families is a different universe. They really, you know, I have papers that show, and I've been on papers that show that not only do these different families have different mechanisms for causing the electrons to pair into Cooper pairs and become superconducting, but even I have one paper with Dirk Vandermeer that going across the doping area changes it. Now let me just also tell you about this dome here. Almost every one of these families of superconductors has a similar phase diagram to this. Okay? This is quantum mechanics. You will find an exception. Okay? But pretty much all the families have something that look like this. And I think I blew it up on the next one. Yeah, so here I've blown this up. And so we have the y-axis is temperature. The x-axis is a thermodynamic variable, typically pressure or doping. You can use magnetic field in some cases. But in any case, on the low pressure, you know, ambient pressure, low doping side of the phase diagram, you typically have an antiferromagnetic insulator, typically. Over on the right-hand side, you typically have a Fermi liquid. And when they cross over, what you have, which in almost every case, above the superconducting dome that I mentioned earlier, you have what I call unsolved quantum matter. So again, the devil is in the details, right? We don't, you know, whether it's dematicity, stripes, whatever, we don't really understand all this, or the pseudo gap. But what I will say is that that's where the interesting part is. And I think my next, or somewhere I have another figure on that, which is, okay, if I get time for my analogy, I'll say this later. For those of you that have ever done any, or actually taken solid state physics, or whatever they call it now, you know that we know how to solve Fermi liquids, right? It's what's in there. Is it gold? Is it silicon? Is it copper? And we just figure out what it is and the crystal structure, and we get the thermodynamic properties, right? We get the optical, transport, and you know, whatever thermodynamic properties from these, you know, DFT, whatever measurements you're using. Okay, that's pretty easy. But and I also want to point out that if you go under the dome, and I've looked at enough of a variety of superconductors to know that you can get those properties too. Okay? We don't know exactly what causes the pairing, but they're still Cooper pairs. All the superconductors to date are still Cooper pairs. So we can use the Bogoliubov-Degen equations and solve what the electronic transport and thermodynamic properties are. And if it's D-wave, you put in a D-wave kernel. If it's multiband, it's a little more difficult, but you can calculate those properties. What you can't do, What we don't know how to do, and there's some progress, is calculating the properties above the dome there. So that's pretty much what I study when I do this work. And so this is just to confuse you, which was that I just threw up a bunch of superconductors up there and showed they all have this dome. So here's the one I showed you earlier, okay? And I'm having trouble with the pointer. Here's the upper left is what I showed you earlier. There's the cuprates, there's organics, there's the dichalcogenides, twisted bilayer graphene. They all show these domes. And what I didn't throw in here, maybe I should have, is that there's this old, nuclear physics plot of the that shows color superconductivity. And so I don't know if you've seen that one, but it's always fun. But this is ubiquitous. This is ubiquitous, but the devil is in the details. What is going on above the dome in every one of these is very, very different, even though they all have this interesting shape. And I also like to point out, and this was, I forget who said this first, it wasn't me, but this dome is so interesting because if you go, it's a dome, which means it's big in the middle and lower on the sides, which means if you're too weakly coupled on the right, a Fermi liquid is a weakly coupled metal. On the left side, you're strongly coupled. If you're an if you're a Mott insulator or a charge transfer insulator, that's as strongly coupled as you can get. So the cuprates, which are charge transfer or Mott insulators, depending who you talk to, they're, it's very strongly coupled. So TC goes down on the right when it's too weakly coupled. It goes down on the left when it's too strongly coupled. These areas are robbing spectral weight from the superconducting area. So, but you need this stuff. You need those strong correlations and this funny stuff to get this high temperature superconductivity. And that's not really understood. What's going on in that delicate balance of the non-correlated and extremely highly correlated electrons. So that's why I think it's so interesting. And then just to show you again, I think you all know some of this. These are just pictures of some of what you can see that I call the unsolved quantum matter. And I'm just showing this again. There's the nematicity on the upper right. There's, I had to throw some of my data in there, so that's mine at the lower left, measuring the nematicity, stripes, charge density waves in the cuprate, charge density waves in the dichalcogenides. You're not going to learn these right now, but I'm just trying to tell you that there are many, many, many kinds of electron correlations that give you this, quote, unsolved quantum matter. So, and besides there being many, many universes of unsolved quantum matter, there are many, many, many microscopes to how to measure these things, right? We have all kinds of ways to measure these things. Some of them are new, like RICS, quantum oscillations to measure the Fermi surfaces. We do a lot at the Magnet Lab. That's a picture on the right there. Some of the work that I do, just understand, and you'll hear about these here, there is a wide suite of measurements, some new and some just greatly improved. There's also a wide suite of calculations that are being created that are astounding. And there's also the quality of the crystals being grown is another thing that's astounding. Some of the experiments that I published on very recently were not even possible 4 years ago. That's how well people are growing the material, so that's pretty exciting. So that's helping us create these. So now I can almost get to do I have a couple more minutes? 7, okay, I could do this in 7, okay. So, so there's unsolved quantum matter, what I mentioned before, Fermi liquids, solved. Fermi liquids, simple metal, we know how to do that. It's the crystal structure and the atoms in the crystal. And we understand how to do superconductors. So let's just put those aside. What we don't know how is to calculate this interesting electron matter or unsolved. So how do we know it's there? So basically, if it's not a Fermi liquid, then the electronic properties cannot be determined by the crystal structure and what's in it, right? Because the electron-electron correlations are so strong. And the second one, which I think of as an experimentalist, is that the electrons break the symmetry of the underlying lattice, right? In the nematic phase, the electrons will pop in like sausages or cigars, depending on what you like, and they're on top of a tetragonal lattice. So the symmetry breaking, and it's just not a solved problem. So moving along here, so conventional superconductors, they're typically less than 40 K, like niobium, niobium-310, and at high temperature, it's solved. It's a Fermi liquid. At low temperature, they're superconducting pairs. So you go from high temperature, where you have a simple Fermi liquid, into a phase transition, it's a real phase transition, right? You're creating and destroying quasi-particles and Cooper pairs. It's really cool. But it's solved. We got this one. What we don't have is this one. So just saying it rather quickly, on the far right side of the phase diagram is a Fermi liquid. And then below TC are Cooper pairs. They may not be electron-phonon coupled, but they're Cooper pairs. So those are solved. Most of the rest of the phase diagram are these interesting problems, which there's success, but there's still a lot of them. We're still working on them. Now, my analogy. So this is just for fun, okay? This is public outreach, and I like to do this. Here we go. So the inspiration was gravity. Actually, before these gentlemen got the Nobel Prize, which was absolutely predicted once they measured the gravity waves, once they did this, I was at a talk that Kip Thorne was giving in Oslo because he just won the Kavli Prize. I was actually on the committee. And he put this picture up there, and he's such a good communicator that I finally got it, right? It's such a great picture, right? What we have is the microscopic theory of gravity is a distortion in the space-time continuum. So then I thought, distortion in the background. And I walked out of that talk, it was a few years ago, and I said, can I make an analogy with BCS? And all my friends thought I'd gone completely crazy. Well, again, I was flying from Oslo to, I think, Denver, which was an applied superconductivity conference, giving a talk there, and I finally worked out the analogy. See, airplanes are really good for something. So this is it. This will give you an idea well, I'll just say this, that it's not a single problem. So let's take a look at LIGO. It was amazing. LIGO measured these gravity waves. Their very first measurement, which I think was, I can't remember, was it 2019? They measured did I do that? They're running out of time. No, they measured, they measured two black holes colliding. Two black holes colliding. The energy of those gravity waves was more than the combined power of all the stars in the universe for light energy. That's a lot, but it's not light, it's gravity waves. And how did they do it? It was this LIGO detector. And this LIGO detector was this kilometer-long interferometers, okay, kilometers-long interferometers that measured the distortion of less than the width of a proton. So let me just tell you, it was like the best $1 billion the National Science Foundation ever spent. It's an amazing experiment. That's their microscope to get gravity waves. It was predicted, we expected they'd see it, and they saw it, okay? Ours is a little different. Our LIGO is not one problem. There are probably 50 kinds of quantum materials that's above those domes and other quantum materials I didn't even touch that we don't know how to solve. So we don't have one question. We're not looking for a gravity wave. We're looking for a multiverse of questions here, where our microscopes are a combination of our materials qualities, our measurement capabilities, and our theoretical prediction analysis. Excuse me. So here's our analogy. Mr. Newton said, okay, we got this one. M1, M2 over R squared. That works. And it does, and it does on the macroscopic level. Mr. Einstein said, wait a minute, there's a few of these problems, like the retrogradation of the perihelion of Mercury, and this isn't quite right. And he came up with the general theory of relativity. And I think he came up with it because, well, he was Einstein. You know, it was really different. And his microscopic theory wasn't just 1 over R squared. It was a distortion in the space-time continuum. To me, one of the greatest successes of LIGO isn't that they measured gravity waves, although that's an astounding success. It's also now, for the first time ever, we have a way to look at the universe that's not light or matter. It's gravity waves. So the big push with people studying this, which I would like to see, is can we understand, using this new telescope, can we get a handle on dark energy or dark matter? I don't know, but that's an outstanding question. And for us, we have Fermi liquid solved, and we have one of the problems solved, which is the BCS electron-phonon theory of superconductivity. Can this plethora of microscopes that we have help us solve our plethora of quantum materials problems? And I've got one more slide before saying goodbye. Okay, 1 minute. So this is just fun, right? Gravity, Newtonian classical. Forces between objects are derived from the mass and their positions, 1 over r squared, and how big the mass is, m1, m2 over r squared. In simple metals and Fermi liquids, the properties are derived from crystal atoms and their positions. So it's kind of an analogy. In the Einstein general theory of relativities, masses create distortion in the background, the space-time continuum. In BCS electron-phonon superconductivity, electrons create distortions in the background. So it's a distortion. But that's just one quantum matter question, okay? So will LIGO help us understand these fundamental questions in cosmology? And will all of our questions, all of our microscopes, help us understand many, many of our quantum materials questions? I'm actually of the belief that you pick one quantum material and stay with it, but that's a belief. And so that's my data. And finally, there's a lot of great questions, and I'm happy to entertain any questions from you. Thank you very much.
Thank you for such a magnificent talk. I think the lecture is open for discussion.
Just don't ask something too technical about gravity.
Yeah, so thank you for a very nice talk and inspirative talk. So the question is, there is some Susskind analogy between wrapped time-space and quantum entanglement. And are you able to map this analogy to superconductivity problem somehow?
I don't think I understand the question. What analogy?
Okay,
you asked me a question last time.
There is a Susskind work about wrapped time-space, right? And then there is a certain analogy of 2 black holes in wrapped time-space with quantum entanglement, right?
Oh, yeah, okay.
But since you are dealing with analogy to general relativity that is also expressed by wrapped time-space, you can think about finding such analogy of wrapped time-space to your quantum materials. Do you have any particular example of that or idea of that?
I don't have any off the top of my head. So how confinement or something? I don't know. You know, when the electrons clump together, you have pneumatic phases or stripe phases. You know, you do have where they clump together, but I don't know if we'd have to think about it. So I really don't know.
All right, thank you.
Okay. Oh, not Valerie.
Laura, thanks a lot for your absolutely beautiful talk.
This is from Valerie.
No. But, okay, no.
Tough guy.
No, but. Okay, come back to slides back.
Oh, wait, I'm going to go the wrong direction.
Oh, wow.
You want this one?
No.
I just want to show my data. Okay.
Where is, okay, here. Okay. Well, I invite everybody
so
to...
what I would like to do is don't ask me questions, because I think you'd rather expound on this.
Oh. Well,
Go ahead.
Okay, I wanted to invite everybody to the lecture by Carla Trugenberger, because this problem to the right completely solved, and this phase diagram is explained in every detail, and all the properties of, for example, pseudogap state are explained also in every possible detail. And it's understood absolutely completely. And one thing, okay, you didn't have time to, you have to confirm that we didn't agree in advance, that you did your beautiful lecture without...
So who solved all these problems? Because I don't...
It's our paper, okay, Christina
Diamantini,
she's here, it's published. Carla will be giving a lecture on that.
Okay, I know the
And
word.
so please come. And
Okay.
there is one property which you didn't have time to mention, and some puzzle. When you have high-Tc superconductors, there is a beautiful property. You make a thin film, one single, cell of them. And Tc of BISCO, for example, is exactly the same as of a bulk material. And it's absolutely understandable, because if you take just the usual, well, maybe it's 1 degree difference, yes, that's true, and 69 instead of 70. If you take the usual superconducting materials, make a thin film, then the Tc can be just 10 times less, and this is quite normal. In BISCO...
Or it can go up.
Huh?
Or it can go up.
Yeah, well, that's okay. And in all the cuprates, it's not like that. And this small thing is explained as well. So, and this phase diagram is completely explained. So, thank you.
Okay.
It's like great advertisement. Thank you very much.
Thanks. I think we have. Thank you. Yes.
Excuse me.
It's okay. The discussion is very interesting, and that's what good about meetings, discussion, you know?
Excuse me, I have to comment on the comment, okay? So the fact that Tc is not reduced in a single atomic layer for superconductivity is completely understood because the Hohenberg-Mermin-Wagner theorem is ineffective for 2D superconductivity. The reason it is ineffective is that there are not enough infrared fluctuations to destroy Tc unless the sample is bigger than the universe. Okay? So there is no reduction of Tc from the Hohenberg-Mermin-Wagner theorem in 2D for superconductivity, because the samples are not big enough for this effect. The theorem is mathematically exact, but the samples are not big enough for this to happen. No, I can give you a reference, okay?
I understand what you're saying. What I'm saying is completely different. You take the usual superconducting material, like lead, or titanium nitride, or whatever. You make them thin film. Their Tc drops 10 times, right?
No.
What?
I don't want to go into a lot of technical details, but no.
Don't know.
You
Well,
know.
it's a lot of...
Tantalum goes up, aluminum goes up. You can lower niobium by a factor of 2 at the most from disorder.
Okay. If you make it thin enough, the temperature drops, Tc. If you take BISCO, the temperature does not. This is the only thing I'm talking about.
Okay.
And okay, that's it. Of course, but it's just one feature.
Yes, please speak on the microphone so everybody online can hear you, like Valerie. Another question or comment? This is a very interesting discussion. This is it's what is nice about meetings. So I encourage you to disagree or agree. I had a question, but it's nothing compared to the discussion. You know, not so interesting compared to the discussion. But there may be some food for thought. When you put this ubiquitous phase diagram, I ask because nobody is asking so far. So when you put this ubiquitous phase diagram, if you put them there, there's a difference between those types of compounds which have a strong covalent character versus the typical solids, metallic or I would say inorganic solids.
So which two kinds of materials? There are going to be differences.
The ones that have a strong covalent character in their bonding, directional bonds, basically, right? So the electronic structure is quite different from the others. And so there seems to be two types of diagrams. in there. Do you know? Have you noticed this? Has anyone noticed this? Or could it be important?
I guess all I can say, I'm going to say something more general than you probably want to hear. But if you look at the low pressure, undoped side, there are many, many different things that are going on there, right? You can have just a bad metal. You could have, all kinds of things. You can have semiconductor-like behavior. So that's just an evidence that, even though they basically pretty much all have the same phase diagram, when you get down to the details, the mechanism is going to be different and what's causing all this. So in other words, YBCO will not have the same mechanism as cerium, cobalt, and Diem-5. It's just not the same mechanism. And if I had time to show you, it looks like the pairing mechanism in cerium, cobalt, and Diem-5 is condo scattering. So even among the heavy fermions, and we can talk about that later, but they're really different. And I just like to point out, people don't like to hear that because they want Occam's razor, they want one solution. But in fact, if you saw how TC fractaled out, there's just too many there. And they're talking about one cure for cancer. Well, there's not one kind of cancer. If you're going to look at different kinds of breast cancer, you're going to have very, very different kinds of therapies. And there's many, many kinds of cancers. So there's not one cancer. The moonshot against cancer, as much as I love Joe Biden, you have to understand that it's very different. And I think that's going to help us solve and learn to create better materials, better superconductors, and better triplet superconductors, which are very hard to design, by understanding each one of these families. So that's my take-home message.
Thank you. Any other comment? Please.
I have a question on your last part of the talk that I found very interesting, the analogy with the deformation of gravity. So maybe, I'm not sure I understand. You think that this deformation can cause some form of pairing that is more stable than BCS or resist?
No, all I'm saying is that no one ever guessed that it was a distortion in the space-time continuum that was a fundamental question of gravity. No one ever guessed that it was a distortion in the lattice, random, time-dependent, that caused superconductivity. It's just basically, I keep saying it's a fun analogy. It doesn't mean that. But it also, I've never had a chance to really look at this more carefully because there might be some ways to help understand these things. For instance, my friends that do quasi-classical theory, right, like Gordon Boehm or some more recent people, David Pines, they were not only studying superconductors and correlated systems in the 50s, they were also using the same equations to apply to the inside of neutron stars. So they were using the exact same equations to look at things that are 10 to the Avogadro's number different from each other in sizes or in energy scales. And so I'm not a theorist. I don't know how to make it any better. It's just a fun way to think about it. And it's to explain that this isn't, our questions in quantum materials isn't a Higgs boson, it isn't a moonshot, and it isn't a gravity wave. There's a lot of them. And one of the reasons I do this is to try to get across that it's really complicated, and we can stay with it. So.
Yeah, because there are works, for example, on graphene from Mediano, in which they show that if you have dislocation, so deformation in your system, then this behaves as an effective monopole. It creates a magnetic field that is like a magnetic field of the monopole, and this can lead to also effect of pairing for superconductors. So what you're saying is very interesting, and in fact it happens that deformation can be interpreted as emergent fields. So it was very interesting.
Thank you that's a great comment. Thank you very much.
I think Professor Gainger has not asked a question, neither made a comment, which is unusual. But if there is any other comment or question, this is the time to ask it.
The best thing is to discuss the issues when taking something together with Laura.
Yeah, I'm feeling really scared that I'm keeping you from your cocktail. I'm really nervous about this, so.
Well, I think we have time. So this is Turkish hospitality, so we can extend and extend.
But there are also disadvantages doing this over drinking, because you may over drink. So I'm not so sure.
I will be okay. So
Okay.
and thank you very much, Laura. I think it's a great honor to have both all the speakers, Valerie, Ahmet, and Hassan Mandal. Also myself, not too bad maybe. Okay, it's your turn now.
Okay, yes, please. I think we have a diploma.
Let us thank one more time to our speaker for the nice speech. And also I should present the certificate attendance. It's necessary for reimbursement.
And we thank all the speakers of this session for making such a nice session. And hope the upcoming sessions will have also such a nice discussion as we have here. Thank you very much for all.
Superconductivity as an intended base.
As what pairs?
There is a terrace bar, just one floor.